Welcome to Foundation Engineering classes by Civil Thinking, and this is our second class on Foundation Engineering. Now before I move on, I would like to tell you that this class is equally important to those students who are studying engineering, foundation engineering or civil engineering in their academic courses, and this tutorial is also important to those who are learning the STAAD Foundation Advanced. Now for better understanding, please watch the video lectures on Foundation Engineering and STAAD Foundation Advanced in sequence as in the playlist so that you understand better, okay? The playlist links of both Foundation Engineering and STAAD Foundation Advanced are in the description. You can watch them from there. Now coming to the today's class. Now in this class we are going to basically talk about the foundation design. How do we design? What are the different methods of design? What are the different types of foundations? Okay, so let us begin. And the first and foremost important thing to learn in foundation engineering is the depth of foundation. Okay, so what is depth of foundation? Now depth of foundation is the depth from the ground level to the bottommost surface of the foundation. Okay, so for example, if we have this ground level and we have a foundation here, okay, and here we have one column, okay, so from here, from the ground level to the bottom, this is the depth of foundation D. Okay, besides that we have this L is the length of foundation, and H is the thickness of the foundation. Okay, and when we look in the plan, this is the section view. Okay, and in the plan view we can see more things, like if I draw a plan of this, so this is the plan view of this footing or foundation. Okay, by the way, this is an isolated footing. Okay, so here we have, this is our column, right? This is our column. Okay, so this is the length of the footing or length of the foundation. This is the width. Okay, the width of this foundation. Okay, now by the way, you cannot see the width of the foundation in the cross section view. The width is inside the paper, right, in this direction, but in the plan view you can clearly see the length and also the width. Okay, so here we have this depth. Okay, now let's move on. Now how much should be the depth of foundation? Okay, now the depth of foundation depends on the soil conditions. Okay, and it also depends on the superstructure load. Okay, so if I write, how do we decide the depth of foundation? Okay, it is decided by two things. First is what? Subsoil condition, and other is superstructure load. Okay, now if I draw if I try to draw a building, superstructure, this is our superstructure. Okay, these are the columns. Okay, and this is our isolated footing. Okay, this is our ground level. Okay, now this is the depth of foundation. Okay, now this is our subsoil, right? Now if you see, now depending on the soil condition, for example, if the soil is weak, okay, for example, if the soil is weak in this region, okay, and then we have a strong strata here. Okay, this is subsoil, but it is strong strata, okay, or a rock bed. Okay, so depending on the soil condition, okay, the soil strength, if the soil is weaker in the top layers, we need more depth so that we can reach a stronger layer. Okay, so if we found this strong layer too deep, so we have to increase the depth. Okay, but if we found this strong strata maybe just a little below the ground surface, then we will, for example, like this, for example, if this is strong layer, okay, then we will keep the depth only up to this. Okay, so here the depth is less, right? The depth is less here. Why? Because a strong layer is found early in the during the excavation. Okay, also the superstructure load, this is the superstructure load P. Okay, if the load is more, we need more depth. Okay, because more the superstructure, more have to more will be the load which will be carried by the soil. Okay, and we need more and more depth. Okay, so we need so the depth of foundation is decided by soil condition and the superstructure load. Okay, so let's move on. Now we have classification of foundation. Okay, now foundations are classified generally into two types. Okay, first is shallow foundation. Okay, shallow foundations are where the depth is less. Okay, and we have deep foundations. Okay, so deep foundations, they have more depth. Okay, and shallow foundations, they have less depth. Okay, as compared to the plan dimensions. Okay, now in the shallow let me show it first here. Now here we could see, for example, if this is the depth, okay, and if we had another condition here, okay, this is our superstructure. Now if they are columns, okay, this is our foundation. Okay, now here the depth is this. Okay, now clearly you can see this is a deep foundation and these two are shallow foundations, right? So shallow foundations, they can be generally they are of two types, isolated and combined, but some books classify them into more. Okay, so isolated, combine. Okay, but in the combine we can have then we also have strap footing. Okay, and we have in the combine we also have mat footing. Okay, now isolated is something when only one column is supported by the foundation. Okay, only this is only one column, this is our foundation, only one column is supported by foundation, we call it as isolated. Okay, this is isolated. Now the combine is where we have multiple columns on the same footing. Okay, so if we have multiple columns, okay, then that is the combined footing. Now mat footing is type of it is combined footing. Okay, where we have the dimensions are approximately proportional. Okay, and then we have these columns are supported on this. Okay, so this is mat footing. And then we have strap footing. Strap footing is when we combine two individual isolated footings, okay, using a strap. Okay, strap is like kind of beam. Okay, so if this is one one isolated footing, okay, and this is other isolated footing. Now when you combine them with the help of a strap, okay, we call this as strap, so it becomes strap footing. Okay, now let us move on to the deep foundations. Now in the deep foundations we can have again where the depth is large, right, the depth is large, okay, large depth. So here we can have pile foundation, we have pier foundation, and we can also have caisson or wall, foundation. Okay, now let me show them here. Okay, let me write here deep foundations. They are, first is pile foundation. Okay, now what is pile foundation? Where we have cylindrical long piles. Okay, for example, this is our ground level. Okay, now for example here we have strong strata. Okay, below ground level is the subsoil, and here we found strong soil. Okay, strong bedrock. Okay, so if we drive thin and long, okay, piles, okay, we call each structure as pile. Okay, so we drive these piles inside, they are tearing the weak soil until they reach the strong strata. Okay, so these are piles. Okay, they can be circular cross section, they can be square cross section. Okay, and they can be they are made up of, for example, concrete. They can be made up of steel. Okay, concrete or also steel, and also wooden. Okay, so they are long. Okay, so that this is the depth of foundation. Okay, so they are long and cylindric means they have very small cross section area. Okay, so that was about pile foundation. Okay, then we have pier foundation. Okay, pier foundation, I don't know how you pronounce it. Okay, now instead of these too many a group of piles, because piles are usually used as a group. Okay, now instead of a group of piles, I can do one thing. I can excavate the ground up to the strong strata. Okay, I can use I can excavate. Okay, and I can use a solid pier. Okay, so what is the difference between pier and a pile? Pile is thin and long, but pier is, it has a large cross section than the pile. Okay, and piles are used in the groups. Okay, by the way, the pile is also solid. Okay, it is not hollow. Okay, that was pier foundation. Then what we have caisson or well foundation. Now as the word well says, how does a well look like? It is hollow, right? So it is like a caisson but hollow. Okay, but hollow. Okay, so this is our caisson. Okay, it is hollow inside. Okay, So this is case and foundation. Okay, so let us move on. Let us talk about the method of foundation designs, because we have to design a foundation, right? So we generally have two methods. Okay, we generally have two methods: rigid method, okay, then we have flexible method, but we also have a third kind, but it is it is not used too much. It is used only during the under special circumstances, okay, and that is truss analogy. Okay, truss analogy. Okay, but it is not used too much, but generally rigid method and flexible method are mostly used, okay, because this truss analogy method, okay, it is complicated. Okay, it is complicated. Okay, now in the rigid method, what do? We will talk about rigid and flexible method, okay, but what is where is it used? It is used if plan dimensions are proportional to depth of foundation. Okay, so what I mean by this is, for example, if this is an isolated footing, okay, let me draw a plan view here. Okay, now let us say this is the ground level, so this is the depth, this is the length, okay, rather I will show it here. This is the length of foundation, this is the width. Okay, now if you see length and the width are, they are proportional to d. Okay, what does it mean? If they are approximately equal, okay, if they are equal, okay, so we use rigid method. Okay, and we have flexible method. When do we use? We use this method when plan dimensions are large. Okay, so for example, let me show it here. Okay, now this is the depth of foundation, right? Now if I draw it as plan, so this is the length, okay, this is the width. Now from here you can see the length is larger, right? Length is too much greater than the depth of foundation. So in such scenarios where the length is more than the, or the width is more than the the plan dimension depth of foundation, so in that case what we do, we use flexible method. Okay, so what we do in the flexible method, so this is, for example, here we have, this is subsoil, right? This is subsoil, and we have all of this. It is this one, this is the contact surface between the foundation and the subsoil. Right, now what we do, we use finite element method, and we we divide it into finite elements. Okay, and we get nodes. Okay, you might if you are a student with finite element background, okay, you might know these. We get these nodes. Okay, by the way, if you want to learn more about finite element analysis, I have already created video lectures. You can find them in my playlist, but to be honest, you don't need much detail here. Okay, when there is a real need of the finite element method, then I will inform you, but right now you don't need to watch the finite element lectures. So in the nodes, below the nodes we have subsoil, right? And the subsoils are, each element is treated like a spring, okay? So okay, so every soil element below the nodes are treated like springs of of constant K, okay, right? So we call this as what? Stiffness constant, okay? So this K of this soil, because we assume the subsoil is element is made up of this, the spring is made of subsoil, so the stiffness coefficient of this, or the spring constant of this spring element made up of subsoil is equal to subgrade modulus, okay, or soil modulus, okay? So these are the things when we begin actually the the flexible method. This is just an introductory class, okay? So when we begin in depth the rigid method and the flexible method, I will definitely talk in detail about this, okay? Now let us talk about truss analogy. As I have told you, it is complicated, but still I think it is appropriate to give a little introduction. So what we do, we treat, for example, this is our foundation, right? Let me use deep foundations, okay? For example, a caisson, okay? In the caisson we have, for example, reinforcement, right? We have reinforcement everywhere, right? We have vertical reinforcement, right? We have horizontal reinforcement, right? And we have concrete, right? Concrete, and we have reinforcement, okay? So what we do in the truss analogy, we analyze it, although it is like a truss, okay? So we assume it like a truss, although it is not a truss, but we treat it like a kind of virtual truss, okay? And when you look at some typical trusses, we have tensile members, okay, and we have compression members, right? So the reinforcement, for example, if this is a tensile member, so this tensile member represents the what? Reinforcement of the foundation. And for example, this one, this is the compression member. So the concrete, it represents the concrete, okay? So the tensile members represent the the reinforcement of this foundation, and the compressive members represent the concrete of this foundation, okay? Then we analyze this truss, okay, to get the to design the foundation, okay? So this was a simple introduction, okay? So let's move on. Now let us talk about design of shallow foundations, especially the isolated footing, okay? But remember, this is only an introduction, okay? So I will highlight only the broad steps here. So let me tell you, let me write any foundation, okay? So all kind of foundations generally have have two broad design steps, okay? So we have two broad design steps when we design any foundation, not just shallow or isolated footing, but all kind of isolated and deep footings, okay? I mean isolated or combine, or the deep foundations like pile foundation, well foundation, okay? All the foundations, we have two major steps, okay? So the first step is always the service design, okay, and the second step is section section design. Okay, service design and section design. Now what we do here in the service design, okay, first of all let me tell you, we use unfactored load cases, okay, or service loads. That's where the name comes from. Okay, service design means we use service loads. What are service loads or unfactored loads? We in designing of any kind of structure, we use factored loads. Okay, like we increase the load by some factor, we call that as factor of safety. Okay, but when we are in the service design, we do not increase the load by some factor. Okay, so we use unfactored. Okay, and but when it comes about section design, we use factored load. Okay, factored load or ultimate load. Okay, and this is the reason section design is also called as ultimate design. Okay, now in the service design, we generally get what we get the the dimensions which are visible in the plan. Okay, so I can write plan dimensions. Okay, when we design, we get the plan dimensions. Okay, what are the plan dimensions needed for our foundation? And in the ultimate design or section design, what we get the section dimensions. Okay, besides that, we also get the reinforcement. Okay, since we get the section designs, okay, dimensions, that is why we have this name here, section design. Okay, so let me show you here plan. So this is a plan. For example, we are talking about isolated footing, right? So this is the length and this is the width. Okay, so when we do the service design, we will get these length and the width of our foundation. Okay, and when we draw the section of our isolated footing, what we have the thickness of it, right? The thickness of the foundation, right? And we have the reinforcement. Okay, the reinforcement. So in the section design, we get the section dimensions like thickness. Okay, and also we get the details about the reinforcement. Okay, so let me give you the broad steps of service design and the section design. Okay, so let us first talk about service design. Okay, now in both the design, okay, both the designs, we carry out checks. Okay, and also here we carry out checks. Okay, so that our foundation is strong, it is safe, it is reliable. Okay, so we carry out these checks. Okay, so in the service design, what is the first check? Check number one is the pressure on subsoil should be less than the bearing capacity of subsoil. Okay, so let me to illustrate this, let me draw a section view. So this is our isolated footing. Okay, now it is resting on what? This is the contact surface. This is the contact surface between what? Subsoil, right? Subsoil and foundation, right? So the load will be, this will be the load from the superstructure above, right? This is superstructure load. Okay, now because the foundation is buried, right? I don't know how you pronounce the word buried. Okay, I'm sorry. It is in the this is the ground level. Okay, and we have here, for example, this is the depth of the soil, but which soil? Above the foundation. Okay, so it also exerts some load on the foundation. Okay, now this is the soil below it. Okay, so what will be the total loads on this soil? Total load on subsoil is what? Is first the load from the superstructure, right? Then we have some additional loads, right? Then we have the weight of the footing, right? Weight will act where? Weight will also act on the subsoil. So WT, okay, weight plus, now this soil, the weight of this soil, we call this as surcharge. I don't know how you pronounce that. WQ, okay. Okay, and we have the weight of foundation, right? So this will be the total weight on the subsoil. Okay, now all of this weight is going to exert a pressure on this soil, right? So the pressure on the soil is what? Subsoil is what? What is pressure? Pressure is load divided by the normal area, right? So it is P plus, let me call WT and WQ as PA, okay, additional pressure. So it is P plus PA divided by area. Now how much is the area? We can find the area from the plan view. Okay, this is the length of footing and this is the width. So what is the area? L times W. Okay, so this is the pressure on the subsoil. Okay, now since according to Newton's third law, the pressure, we can, there is equal and opposite reaction. Okay, so when we see the superstructure and the foundation and all this surcharge, it exerts a load on the soil, we also say it exerts a reaction force on this, okay, or reaction pressure. Okay, so this is the pressure diagram if the pressure is uniform. Okay, this is the pressure exerted by the soil on the foundation, okay, as a reaction. Okay, so it means the same equal amount of force is exerted by the what? By the everything above the soil. Okay, the footing and the surcharge and the superstructure load. Okay, so this pressure should be less than, okay, or equal to bearing capacity of soil. Okay, we denote it with G. Okay, so P should be less than or equal to G. Okay, so this is the first check. Okay, now since P is equal to P plus PA divided by L times W, right? So this equation is going to, of course it will try to give you these values. Okay, so if you want to find these values and the the total load and the bearing capacity of the soil, and you want to know what should be the plant dimensions, okay, so you can use this equation, you can get these variables. Okay, I mean it is going to be at least equation number 1, okay, because we have two unknowns. Okay, then you can use another equation to get the another equation. Okay, because we have two unknowns, we need two equations. Okay, so this is your equation. So this is the reason I have told you earlier that this service design, it is going to give you the plant dimensions, okay, because the plant dimensions are included in the service design, okay. So this is the check 1. Okay, now let us talk about check 2. Check 2, what is the check 2? Now before we talk about check 2, I remember something I should discuss that, since we discuss about this this pressure diagram, right? This is the pressure diagram, okay, pressure diagram, okay. Now let me talk about a few kind of pressure diagrams, because here the pressure is uniform, so you get a rectangular pressure diagram, okay, but it is not always true. You may get some other shape. What we call that is, you might get shape like this, okay, or you can get shape like this too, okay. So let us talk these about pressure diagrams, okay. So the case 1, we can get multiple kind of combinations: load plus uniaxial moment, okay, and we can also get load plus biaxial moment, okay. Now what is this? Now as you can see here, we only have this much of load, right, P, and there was also PA, okay. So earlier we only show this much of load. It was P from the superstructure, and I can add also PA here, so that I can show the total load here, okay. But in some cases you might get a moment too, okay, moment too. But why? Because of the soil pressure, okay. So for example, this is the soil pressure here, okay. This is the soil pressure, right? This is on the contact surface. So if the pressure is not uniform, you will get a moment, okay. For example, the pressure on this side is more. Let me show it like this. The pressure on this side is more, okay. So if I draw a diagram like this, you can see the pressure to the left of this green line is more than this, okay. So it means the net pressure is towards left, okay. So the net pressure, because force is pressure, let me show you. Pressure is what? Force divided by area. It means force is pressure multiplied by area, okay. So since the net force is in this direction, you might get a moment, okay. So because it is only because of the one side, right, so we call it as uniaxial, okay. So because of this moment, okay, you are going to get some minimum pressure, okay, P minimum, and here you are going to have P max, okay. But early it was only like this, right? Here it was P and here it was P, okay. And what was the value of pressure? Pressure was P plus PA divided by what? L times W, right? But here, because of this moment, you will have more pressure here and you will have less pressure here. So if I find P minimum, it is going to be pressure of due to this, right? So it is going to be P plus PA divided by L times W, okay. So let me show it here. This was L, this was W, right? And then we have to subtract something, right? Originally it was all of this, okay. So from here to here, it is this, right? P plus PA divided by L times W, okay. But we have some decrease due to this moment, okay. Due to the moment, we have this much of decrease here, okay. Now how do we find the pressure because of moment? Do you have any idea how to find pressure pressure from the moment, or stress, because stress is same as pressure, right? So how do we found the this decrease in the pressure, right? But because this much is the pressure due to the moment, okay? So we can use we know the equation of bending, m by ei equal to E by R equal to sigma by y, right? This is bending equation, okay? Now we don't need this part, so we get this. Now this sigma, it is the stress or the pressure, okay? So we get stress to be this, right? So this is the stress because of m moment, okay? So here this part is what, minus my by I, okay? Why? Because originally it should be like this, okay? Uniform, right? This was the pressure P, right? P, and what is the value of pressure of P? It is P plus PA. Let me denote the pressure with PR, I think, okay? So L times W, right? It was the pressure. Now because of the moment we got some decrease, okay, and we also got a proportional increase, okay? So here you can see this much, it is the decrease, okay? So only the pressure diagram is this, okay? So we got this pressure. So this much of decrease here is why? Because of the moment m, right? Because of this moment m we have this much of decrease, right? Let me show it here like this. This much is a decrease due to the moment m, okay? And this much is the same amount of increase, okay, because of the m, okay? So from here this is the P max, okay? So this was P minimum, right? So it is total minus this one because of the moment. So I wrote this, total is this, right? This is the total, P plus PA by L minus decrease minus my by I, okay? Now here what is the total? It is P plus something, right? This one is because of the movement. And what is the movement due to this? What is the pressure due to the movement? It is my by I, right? So this much is my by I, okay? So P max is equal to this pressure PR, okay, plus my by I, okay? So it is P plus PA divided by LW plus my by I, okay? Now if I summarize it, so this is our isolated footing, right? Now if we have this if we have single load, right, P plus PA, I mean without any movement, then the diagram is, pressure diagram is this, right? And what is the value of this pressure? It is P it is equal to P plus PA divided by LW, right? Now if we have if we have P plus PA and we also have a moment, okay, then what is going to happen? Let me write it here. If we have a moment, okay, we are not going to have this, right? We will not have this, but we will have this, right? So this is our pressure diagram, right? And we have, this is P max and this is P minimum, okay? So here P max is what? P plus PA divided by L times W, this much P, and plus due to the moment m, okay? And this is my divided by I, okay, where I is the moment of inertia, okay? And we have this P minimum, it is P plus PA divided by LW, let me write it clean, P plus PA divided by L times W minus my divided by I. Okay, so in the max we have plus sign and in the minimum we have minus sign. Okay, now we can also have, this was uniaxial. Okay, now we have biaxial. Okay, so the same way we have this moment only along y, for example one axis, this was movement along one. Now because we can have multiple axes, then we can also have movement about the another axis. Okay, so that is biaxial. Okay, so let me show the biaxial here. So P plus PA. Okay, we can have, for example, let us say this is x axis and this is z axis. So we can have, this was only about one axis. Okay, for example this was about z axis, so we only had mz, but we also have here about the x axis, so we have mx mz. Okay, so here we are going to have the value of, so here we are going to have the value of p, max. Okay, P plus PA divided by LW plus MZ YZ divided by IZ plus MX YX divided by IX. Okay, and we are going to have the P minimum. Okay, same. Okay, same thing. Same thing, but here it is going to be a negative sign. Okay, so anyways we have done one step. Okay, in the service design I told you there are checks. Okay, we talk about one check. Okay, it was about the bearing capacity of soil. Okay, and we got one equation from here and it is this. Okay, now if the pressure was not uniform, then you will apply more, all of that equation what we discuss here. Okay, for example this P minimum. Okay, this P minimum, it has to be less than or equal to G. Okay, anyways we talk about the shear capacity, this bearing capacity of the soil. Now we will go into the check 2. Okay, check number 2 in the service design, right? So what is the check 2? It is the check for sliding. Okay, now when does this happen? It happens because of the lateral load. Okay, now if I show you now for example this is our superstructure. Okay, now we can have wind loads, right? They are horizontal, right? Wind or even the earthquake or seismic loads, right? So we have these, we call them as lateral loads. Okay, lateral loads. Okay, now what they can do, because they act, we can find, we can write them here. They can kind of try to slide. Okay, slide the foundation. Okay, to, for example if it is acting towards the right, so they might slide it. Okay, so what is holding it? This is subsoil, right? But what is preventing the slide? It is this friction force, right, between the subsoil and the what, and the foundation, right? This is the foundation, right? So this friction force, it should be enough to resist these lateral loads, right? So what is the value of friction force? Now we know the friction force depends on the normal load, right? For example this is P. Okay, and I told you there is P plus PA basically, right? Because there are additional loads, right? So This is our foundation. This is the contact surface, it is this, right? So on it we have P plus PA, okay. Now the friction force F is equal to coefficient of friction mu times P plus PA, right? And it has to be greater than the lateral loads, if I denote them with PH, okay, P horizontal. So it has to be greater than P horizontal, right? This friction force has to be more than this. Only then the foundation is safe in what? Sliding, okay. So we can write mu times P plus PA divided by PH, right, has to be greater, right, greater than some factor, okay. Because if we if it is like this, then mu P plus PA, which is F, it will be PH times this factor, okay. Now this factor, the value depends on what code you are following, okay. If you are following European code, if you are following the American code, okay, whatever the code you are following, the exact value depends on that. But typically this factor, we call it as factor of safety. This factor of safety is around 1.5, okay. So this has to be greater than 1.5, okay. This is factor of safety, okay. So this was check 2. Check for sliding. What is it? It is this friction force has to be greater than the the horizontal forces or lateral forces, right? So PF should be greater than PH, right? Or PF divided by PH should be greater than 1, or in fact 1.5 typically, okay. So we got this equation, right? So let us move on to check number 2, right? 3. Check number 3 in the service design of isolated footing, right? Check for overturning, okay. Now keep in mind this, the overturning only occurs when there is overturning moment present, okay. In some scenarios there could be possibility that an overturning moment is present, and then only this check is important, okay. So if there is no overturning moment possible, so we don't need this check, okay. So let us assume we have this isolated footing, okay. Now these are our loads, right? Let us suppose we have an overturning moment, okay, PO, okay. Now it is acting in the anti-clockwise direction, so of course we need one moment right here on at this level, okay. For example, we need one moment at this point, right, and it is called as resisting moment, okay. So we need this resisting moment, okay. It has to be equal to or more than the overturning moment, then our structure is safe, okay, against overturning, okay. MR divided by MO, it has to be greater than equal to 1, okay, but typically it should be greater than 1.5, okay, but again this value depends on the code that you are following, okay. So when our resisting moment, what is resisting moment? It is the the opposing moment which acts against this overturning moment, okay. Now let me tell you something interesting, very much interesting here. Here we got this the friction force, right? This is the friction force, right? The friction force F, it is a function of P plus PA, right? Now in the check 1 we got this the maximum pressure, minimum pressure, or in the from the pressure diagram we got the pressure as P plus PA, right? So you can see in the service check, okay, everything is in terms of P plus PA, okay. Now what is P plus PA? It is the total load on the subsoil, okay. So in all the service checks, okay, be it the bearing capacity check, or the pressure check, or the sliding check, okay, or the overturning check. All of it includes the P plus PA, that is total moment on the subsoil. Okay, now let me tell you before calculating the MR, this MR will again depend on P plus PA. Okay, so because P plus PA is the total load on the subsoil, this is the reason we also call the service check as kind of geotechnical check. Okay, because it's more about the soil. Okay, so let me calculate MR. Okay, now this resisting moment, how we get this resisting moment? We get this from the pressure diagram. Okay, so let us say this is our pressure diagram. Okay, so this resisting moment MR, we know moment is force multiplied by what? Force multiplied by lever arm or distance. Okay, now this half of the pressure diagram is going to exert a force in the midpoint. Okay, let us call this as F. Okay, so this F, we know force is pressure multiplied by area. Okay, so if we see the section view, I mean the plan view, okay, this is L, this is W. Okay, now this F is going to be what? But in F we are going to consider only this length, right? This much of length. Okay, so but F acts on the middle of this. Okay, now how much is this length? It is, the total is L, so from here to here it is L divided by 2. Okay, so it is L divided by 2. Okay, but this force acts on the middle of this diagram, right? So F will act on half of L by 2, which is L divided by 4. Okay, so F multiplied by L by 4, it is our resisting moment. Okay, now let us calculate the F here. Now we know force is pressure multiplied by area. Pressure is P plus PA as expected, because I told you everything in service design involves the total load on the subsoil divided by the area. It is what? L times W, right, times A. Okay, now A of what? Area of this. Okay, it is L divided by 2 times W, right? It is L divided by 2 times W, right? So LW and LW will cancel, so it is P plus PA divided by 2. Okay, so resisting moment is F times F is what? P plus PA divided by 2 multiplied by L by 4. Okay, now so it is P plus PA times L divided by 8. Okay, so this is our resisting moment, and it has to be more than what? It has to be more than the overturning moment, right? So all of this divided by MO, it has to be equal to greater than or equal to 1.5. Okay, 1.5. Okay, so this was check 3. So let us move on to check 4. Okay, now check 4 is about what? It is about uplift. Okay, so for example, we have this isolated footing. Now sometimes there might be some uplift forces. Okay, okay, and we should the foundation should be able to resist this PU. Okay, so PU, the P, okay, applied has to be more than PU. Okay, so this is the check against the uplift. Okay, so this ends our what? This ends our service check. Okay, now let us move on to the other check, because I have told you in the foundation design we always have 2 major steps. Okay, 2 major steps. So the step 1 is what? Step 1 is service design, and the step 2 is what? Section design. Okay, so we see all the checks. We saw all the checks in the service design. Let us move to all the checks in the section design. Okay, but keep in mind, what loads do we use here? We use factored loads. Okay, so we multiply the P plus PA with some factors. Okay, and then we use those loads. Okay, so let us move on to the section design. Ultimate design of isolated footing. Okay, so we are going to see the ultimate design of isolated footing, right? Now I have already told you what we do here. We do it is done using factored loads, right? And we also do several checks here. Okay, several checks. Okay, for example, what we do design moment check, we also do shear check, and we do yes, development length check. Okay, now in the shear check we have two checks. We have one-way shear check and we have punching shear check. Okay, so let us talk about these checks one by one. So these are 1, 2, 3 and 4. We have 4 checks in the ultimate design check. Okay, now this ultimate design check, also called what? Section check. Okay, now why it's called a section check? Because we are going to get the using this ultimate design check or section check, we are going to get the dimensions which are visible in the section. Okay, so in the section what is visible, we have the thickness of the foundation. Okay, and also we get what? The reinforcement. Okay, and also we have the depth of foundation, right? Depth of foundation, right? So let us begin one by one. So first is design moment. Okay, design moment. Now why it is called design moment? Because the moment which is used in the design. Okay, so it is also the moment which we get from the factored load. Okay, so we have here this P plus PA times safety factor. Okay, factor of safety. Okay, because in the ultimate design or the section design we always use the factored load. Okay, so in all of these steps we are going to use not P plus PA but P plus PA times some factor. Okay, and that factor, how much is that? It depends on the code that you are following. Okay, but overall the steps are same. So in the design moment, now what do we see in the design moment? We see moment due to pressure of soil. It has to be more than movement capacity of footing. Okay, so we do this check. Okay, so if this is true, if the movement due to the pressure of the soil, I mean it is less than the movement capacity of this foundation, then our foundation is same. Okay, so to illustrate this, let me draw a diagram. Now let us say this is our pressure diagram. Okay, this is pressure diagram. Okay, now also let us draw a plan view of this isolated footing. Okay, Now this is the length L, right? This is length L, this is the width, right? Now the load here is P times factor of safety, right? Because we use the design load or the factored load in the section design or the ultimate design, right? Now this pressure diagram, it is going to exert, a force, okay? If I draw a line here, okay, now we are going to have some force here because of this much part of this diagram, right? So first of all, in the in the moment design moment check, what is we select a critical face, okay? So in the design check, this wall, this face, lateral face is the critical section, okay? So we do the check, this moment check at this section, okay, at this face, okay? So we have to check the moment, okay, at this point due to this pressure, okay? So we only have to consider this much, right? This much of pressure diagram, okay? So force is pressure multiplied by area, right? So what is the area here? Area here is this much, right? This much is the area, right? So how much is it? Let us say we have the the diameter, okay, of the column as, for example, HW, okay? So the total is L, right? Total is L. So L minus HW is how much? L minus HW, total is L and HW is this, right? So L minus HW is this much and this much, right? Now L minus HW divided by 2 is only this much, okay? So we need this length, right? It is what? It is L minus HW divided by 2, and how much is this? It is the width W, okay? So area of this much is, it is L minus HW divided by 2 times the width of the foundation, right? This isolated footing, okay? So this is the force. Now moment is what? Moment is force multiplied by distance, right? Distance. Now this force is acting exactly at the midpoint, okay? So if I show it with this, now this force is acting here, okay? So let me draw a clean diagram. So this force is acting here, okay, right, in this part, right, this force. Now the total here is how much? As you can see here, L minus HW divided by 2, right? So what is the distance between this force and the face? Because this is the critical face, right? We have to calculate the moment here, okay? So we have to find the force multiplied by this much of distance, right? This much of distance, force multiplied by this much of distance is the moment at this critical face, okay? So it is, so the total is L minus HW by 2, and this is only half of it, okay? So it is L minus HW by 2 divided by 2, so it is L minus HW by 4, right? Because half of L minus HW by 2 is L minus HW by 4, right? So we can write this moment is F multiplied by L minus HW divided by 4, okay? So this moment, right, this is the moment from the soil on the foundation, right? This is the subsoil, right? Subsoil, and this force is from the pressure diagram of the subsoil on this foundation, okay? So there must be some, the moment capacity of this should be more than the moment from this, pressure diagram, okay? So this is the check here. So the moment due to the pressure of the soil, it should be less than movement capacity of this footing. Okay, so this way we make sure we are safe. Okay, now the things to be kept in mind here is we have L minus HW by 2. Okay, now H minus this HW is the width of this column. So as I have told you earlier, in this ultimate design we get the dimensions visible in the section view. Okay, and in the section view we also have the width of the column visible. So be sure when you apply the moment check, you are going to get this the width of the column section. Okay, now also from this equation, when you equate this, moment is less than or equal to mc. Okay, now mc is the moment capacity. Okay, moment bearing capacity of the foundation. Now the moment is resisted by the reinforcement, right? We know the moment is resisted by the what? Reinforcement, right? So this moment capacity, it involves it is a function of reinforcement. Okay, amount of reinforcement. Okay, the area of reinforcement. So from this equation you will also get the required area of reinforcement. Okay, so that's why I have told you in the design, in the ultimate design, we are going to also get the amount of reinforcement. Okay, so this was the check 1, right? So let us move on to the check 2. Okay, check 2. So what is the check 2? Check 2 is the shear check, and in the shear check we first have one way shear check. Okay, now one way shear check, it is called one way because we only consider one side. Okay, in this. Okay, so for example, let me draw an isolated footing. Okay, now this is P times factor of safety, right? So this is our pressure diagram, right? This is the pressure on this contact surface because of the subsoil, right? Now as in the previous movement check, I have told you, for example, let me draw this face was the critical section, right? Critical section for what? For movement, right? Now you can see this, because of this pressure, I have told you that we get a force here, right? Because of this pressure we get a pressure force on this foundation, on this isolated footing. So it not only exerts a moment, okay, moment on this critical phase, but it also exerts a shear force. Okay, so we also get some shear force. And where do we calculate the shear force? We calculate it again as we found the moment on this face, as we treated this as the critical section, but in the shear check, what is the critical section? Critical section is at some distance d, okay, from the face. Okay, now again, how much is going to be d? It again depends on the code that you are following. Okay, but this is our critical section for shear. Okay, shear. So we have to find the shear force on this. Okay, we have to find the shear force on this. And how do we get the shear force on this? We get it from this much of area, right? So this much of area of this pressure diagram is going to give us the shear force on this section at a distance of d from the face. Okay, so in order to get this area of this pressure diagram, right, we have to draw the plan wave, right? So if this is the plan wave, for example, okay, now this is our critical phase, right? It is, how far is it? It is at a distance of d from the face, right? So the total is L, right? Let us say it is HW, the thickness of the column, right? So we have to find this much of area, right? Okay, so this much is the area that we need to find the shear force at this critical section. Okay, now to find the area, how much, what we need this width. We know already this is W, but we need this length. Okay, so let us calculate this length. Okay, now as I already told you, the distance between this to this is L. So if I subtract HW from L, we are going to get these two distances. Okay, so L minus HW is going to give me these two distances, but if I half it, L minus HW by 2, so it is going to give me 1/2. Okay, so we already know this much, right? We already know this much. We already know this much, L minus W by 2, right? But we need only this much, right? So this is D, right? So how much is this? It is L minus W by 2 minus D. Okay, so now we know this dimension to L minus W by 2 minus D. So now we can find the area. Area is going to be W times L minus W by 2 minus D. Okay, so from here we will find the shear force. V is what? V is L minus HW by 2 minus D, right, multiplied by width W, okay, times pressure, right? Because this pressure multiplied by this area is going to give me the shear force at this critical section, which is at a distance D. Okay, so we got it, L minus HW by 2. Okay, so this was not L minus W, it is L minus HW, right? HW, right? Why? Because this much is L minus HW divided by 2, and when we subtract this D, we will get this much of distance. Okay, and this is what we need to calculate this area. Okay, so the shear force is pressure multiplied by this area, so we got the shear force. Okay, now we have to find the shear stress. Okay, shear stress tau. Okay, and it is going to be shear force divided by area, right? But which area? Not this area, right? Because in the, when we calculate the shear stress, we have to find the area which is parallel to the shear force. Okay, now this area, it is perpendicular to the shear force, right? Now how do we see? Now if I draw, try to draw it in the 3D, right? Okay, now you can see the shear force is here, right? This is the shear force V, right? V, and where is it? It is parallel. It is parallel to section here, right? I mean like this, right? Exactly like this area, but here, right? Here, okay? Here, right? So this is, for example, let us assume this is here. Okay, so if this is shear force, this is shear force V, and what is the area? Area is, now the thickness of this foundation is T, for example. Okay, now what is the width? Width of this, width is W, right? Width is W, so this is W, right? So I can show it here. So this is width W, and T is the thickness. Now what is the area? This is going to be the area, right? So the area is T times W, right? So I can write the shear stress to be all of this, okay? All of this divided by area is T W, okay? So this is the shear stress, okay? Now at this critical section, the shear stress should be what? It should be less than the what? The bearing shear capacity of the footing. Okay, so this tau should be less than or equal to tau. For example, if I denote it with tau naught, okay, this is the shear bearing capacity of foundation. Okay, now if you look at this, you can see all these dimensions are involved in this formula. So HWD, right, all of these things, when you apply the shear check, you will get these, especially the thickness, right, the thickness, because thickness is involved here, as you can see, thickness, okay, and also the width. So you are going to get this thickness and the width too, okay, especially the thickness, because we are already assuming some width of the foundation often in the projects, but the thickness is important, and we will get this thickness also from the shear check. Okay, so this was about the one-way shear check. Okay, so I told you in the shear check we have two shears, one is one-way shear check and another is punching shear check. Okay, so we'll talk about check 3. Check 3 is punching shear check. Okay, now let's talk about this. Now, unlike in the in the one-way shear check, we only found the we only found the shear stress only on one critical side, right, in the one-way shear check. Okay, but in the punching shear, we found the shear stress on all the three sides. Okay, so around all of this, okay, around all of this column, we will find the shear stress at some distance from the face of the column. Okay, so if it is like this, okay, now let me draw one critical section here. Okay, this is one critical section, this is another critical section. Okay, now behind this, okay, behind this, this is the behind part of this column, and in front of this column, this is the front view, right? So we also find the shear stress on these cross sections. Okay, as you can see by the green lines, we do the shear check in the all the four sides. Okay, now this is called a punching shear stress, because basically what happens is, because the column, if the shear capacity of this footing is not enough, so what happens is, let me show it here. So this is the column. Okay, now if the shear capacity is not enough, the column will punch inside. Okay, as I have told you in the previous class, it will punch, it will tear down the the foundation, and it will get inside it. Okay, so the only thing which is resisting this this column not punching inside the footing is the shear resistance on all the four sides. Okay, so that is the only thing which is keeping this column not punching into this. Okay, so the shear strength on all the four sides around this column we have to calculate. Okay, so around the column we will check shear strength around these. Okay, so they have to be more than the the critical shear, right, or the shear capacity of this concrete. Okay, so now we, as per the codes, different codes, we found the critical section, right? These are all these green lines, they are the critical sections where we found. Okay, and the distance is D effective. Okay, and how much is the value of D effective? It depends on the code that you are following. Okay, so the code decides how much is it going to be. Okay, but what we know is it is the distance from the face of the column, okay, to some distance. Okay, the critical section is located at some distance from the face of column, right? That is what we know. Okay, and how much away, that depends on the code. Okay, so let us write. So what we do in the punching shear check, we know shear force is what? Pressure times the area, right? Pressure times the area, right? So this is the normal area. Okay, so we need all of this area. Okay, all of this area to calculate the the shear force on all the four sides around the column. Okay, so this is the hatched, this is the area, this hatched area. Okay, that's what we need. Okay, so we need this area of hatched part, right? Hatched part, right? So that is going to give us the shear force. Okay, now when we talk about the shear stress, but punching shear stress, it is going to be this shear force V divided by what? Area. But which area? I told you the shear stress in the, when we calculate the shear stress, we found the area parallel to the shear force. Okay, so parallel to the shear force is what? It is, shear force is this, for example here, right? So this area, this length times inside, it is going to be the area. Okay, similarly here the shear force is here. What is the parallel area? Parallel area is, for example, this, right? Similarly on behind. Okay, so if I draw this in 3D, we will understand. So let me draw it in let me try to draw it in 3D. Okay, so it is something like this. Okay, so no, this side, okay, all of this side here, it is this. Okay, this side. Okay, so this is this side. Okay, and this is what? It is the thickness of foundation. Okay, because we have to find area of each, so it is this thickness, right? So this is the thickness, right? So this is going to be the thickness. So it is on this, it is on the all the four sides. Okay, so from here we will find the area. Okay, area of this face, area of this face, plus area of this face, plus area of this face. Okay, by the way, this area and this area is same, right? For example, in case of a rectangle, because this length is same as this. Okay, so in the 3D, the area of this section is going to be equal to area of this section. Similarly, this length is equal to this length, so the area of this section is going to be equal to area of this section, right? So we will find only area of this and multiply it with 2. Okay, and then we will find area of this and multiply it with 2. Okay, so from here area is going to be, now let us say this is L dash, this is L double dash. Okay, this is L double dash. Okay, okay, for example, this is L double dash, this is L dash. So area is going to be this thickness T, right, times L double dash plus thickness times L double dash plus thickness times L dash plus thickness times L dash, right? So we can keep T as common, so it is going to be L dash plus L dash is 2L dash plus L dash plus L dash is 2L dash. Okay, I mean L double dash plus L double dash, okay, is 2 double L dash. Okay, so this way it is the area, and we can use this here. Okay, so we can write it as T times, or we can also put 2 as common. Okay, 2 as common. Okay, so it is going to be T times L double dash plus L dash, right? L dash plus L double dash, it is going to be the area. Okay, so this will give us the punching stress, and it should be, punching stress should be what? This punching, this shear stress in punching should be less than or equal to the shear capacity of the foundation. Okay, then only it is safe. Okay, so this is the punching shear test. Okay, now keep in mind, in the euro codes, okay, in euro code we find the punching shear test at two places, okay. As per the euro code, what we do, we found the for example, in here, what was the critical section? Critical section was at a distance of d effective, right, from the face of the column, okay. But the euro code suggests something else. The address, it says one critical face for the shear check is the face of the column, okay, itself, face of the column, as in the moment, design moment check, and also at some distance which is equal to 2 times d effective, okay. So we do it 2 times in the euro code, as per the euro code, okay, but same procedure, but we do it 2 times, and also the location of the critical sections is different, okay, for the punching shear, okay. So this was about the punching shear, okay. So let us move on to another check. So what do we have? So this was, let me see, this was check 3, punching shear test. Now let's write check 4, and this is about what? Development length, okay. Now we do this check to avoid the loss of bond. For example, in the let me draw it here. Let us say this is isolated footing, okay. Now we know we have the reinforcement, okay. For example, the reinforcement, okay, we have the reinforcement like this. So the reinforcement have two bonds, okay. So first is this, the lap length, right, between what, between two these reinforcement bars, okay. There is a bond, okay, and there is also a bond with the concrete and the reinforcement bar, okay. So we do the development length check to make sure our bond is strong, okay. But keep in mind, this is not compulsory, but although it is important, but it is not mandatory. So this was it was all about the design of isolated footing. We saw the service design and we saw the section or ultimate design, okay. So I think this is enough because the lecture is going too long, okay. So if you have any doubts, you can comment or you can also contact me, okay. So that's it for today. See you in the next class. Thank you.